Welcome everybody to the Bioexcel webinar number 86. Today we have a presentation on MiMiC. MiMiC actually is an high-performance framework for multiscale molecular dynamic simulation. The presenter of today is Andrei Antalik from the L'École Polytechnique Fédérale de Lausanne, and he will tell us about MiMiC indeed. I'm hosting this webinar. I'm Alessandra Villa, and together with Otto Andersson and Richard Norber, we are hosting this webinar for Bioexcel, that is the Center of Excellence for Computational Biomolecular Research. This webinar is being recorded. During the webinar, you might want to ask some questions. You are most welcome to use the Q&A function. Please type your question in the Q&A function. And then also, if you tell us if you have or not a microphone will help, since at the end of the presentation of Andrei, we will ask you to unmute yourself. So I will unmute you so you can ask yourself the question. And in case you don't have microphone, I will read the question for you. So after the webinar, maybe you still have some questions, so you're most welcome to join the webinar category in the Ask Bioexcel forum. Here is the barcode, if you want to scan it. And then ask your question to the post by answering to the post of Andrei speaking about this webinar. Andrei will be available next week, all next week, to answer questions. Okay, something about Andrei. Andrei Antalik was graduated in chemical physics at the Charles University in Prague, where he also obtained a PhD under the supervision of Professor Pittner. In 2021, he joined the group of Professor Ursula Rutzlisberg as a postdoctoral researcher. His research focused on the development of electronic structure and multiscale method, and is one of the main developers of MiMiC. And now he will tell us about MiMiC. Now I stop sharing and I leave you the word, Andrei.
Right, so good afternoon, everyone. Just a sec. All right, again, good afternoon to everyone who decided to watch this or spend their afternoon watching this webinar. Thank you, Alessandra, for the nice introduction, and especially I'm grateful for the opportunity to talk to you a little bit about MiMiC. And I think that right now it's like the perfect time to do so, because over the past few years we have made quite some progress with the framework, and I really hope that soon we'll be able to release it into the world and let people use it, and those who would be interested also to contribute as developers. But before we get to the actual contents of the presentation, I would like to start with a short introduction and motivation on why we even need multiscale models. So as you might know, many natural phenomena, especially in chemistry, unfold on different scales in time and space. For some, you may description of some, like, for example, chemical reactions where there are transfers of protons or electrons, you might require quantum mechanical description of these processes. Then there are systems like proteins, to study properties of which all you need is classical description through molecular mechanical model, something like a classical force field. And for some other properties, you can resort to even cruder description by coarse-grained force fields. But there are specific situations where and a good example of those are, for example, enzymatic reactions, where you would really like to study what's going on at the active site of the enzyme. But you also know that the environmental effects and the structure of the entire protein might affect the way the reaction unfolds. And okay, naively, I'm pretty sure most of you are not that naive, but naively you might say, yeah, so let's just apply the QM method to the entire enzyme. What could go wrong? But you would really quickly discover that the unfavorable beating of these QM methods, the unfavorable scaling of these methods would beat you down and you would get nowhere. So since these processes are kind of spatially constrained, so the reactions happening in the active site, we can resort to these multiscale methods, and probably the most popular of those is QMMM, combining the QM description. Here, it would be applied for the spot where the reactions happening, and we will describe the rest with just classical model. From software development perspective, it's also interesting to think about how we could implement these models. So as computational chemists or biophysicists, you're pretty familiar with plenty of very specialized computational chemistry software for electronic structure calculations, for molecular dynamics, and so on. But typically, there's one primary type of methods that these software packages focus on, and the kind of straightforward way how you could implement the multiscale model, and as I still use QMMM as an example, is to take this program specialized on QM and add a functionality that it lacks. So here it would be the molecular support for MM and classical force fields. And then, of course, you need to take care of the interactions between the two subsystems. Another more flexible approach is to write an interfaces between these programs, each specialized in something different. And the actual data transfer could be handled by I/O operations, meaning you're writing input files, reading output files, and so on. It could be something more sophisticated, like transferring data through network, and so on. Or alternatively, you can compile one of these programs as a library and then access its functionality by linking to this library from the other program. I think the most interesting one are these integrative frameworks which create these bunches of loosely coupled programs and then handle the interactions between subsystems, data transfer, and so on. And there are many pros and cons to these different approaches. I'll just say that when we talk about MiMiC, it will be the last example I gave. All right, so as I said, MiMiC is one of these integrative frameworks. It is an open source project and that loosely couples these external programs that are, so for example, QM, MM, and so on. And it does it by adopting this multiple program, multiple data model. And the reason for this is that often the effects of these types of setups or settings are kind of detrimental to efficiency. And we aim to run these external programs as efficiently as possible while remaining the high degree of flexibility in choosing these different components for simulations. So typical simulation on a multi-layer subsystem, here represented by two layers, goes as follows. You define these individual subsystems in these external programs. You launch the simulation, and meaning that these programs run concurrently and mimic during the individual steps, because we're focusing on molecular dynamics. So transfers the relevant data that it requires for a given step, and then computes the interactions between the subsystems. This way, we prevent the repeated shutdowns and startups of these external program, which would have real detrimental effects on the performance, especially when running in these highly distributed HPC settings. So since the QMMM is the most prominent of these multiscale models, as I already mentioned, and at the moment it's actually the only one we implement in MiMiC, first I will describe how we do this. Then I'll give you like brief overview how it feels using MiMiC from the perspective of a user. We'll look at certain aspects of its performance. For those of you who'd be interested, I'll talk a little bit on how it works under the hood, and I'll list a few features, either current or the one that we plan to implement soon. So let's start with the QMMM. So in QMMM, as I already foreshadowed in the intro, we split the system into two parts, rather small QM subsystem that is treated at the QM level, and then the rest of the system that is treated with classical force field, or MM. And there are different ways or different schemes how you can implement these the QMMM models. One is so-called subtractive scheme, where you compute the contributions to forces and energies at the QM level of the QM subsystem only. Then you evaluate the MM, or you evaluate MM forces and energies of the entire system, including QM subsystem, and then you subtract the contributions of the QM subsystem at the MM level only to avoid double counting. The different approach that we implement in MiMiC is this additive scheme, where you evaluate the contributions of these individual subsystems and then compute the interactions between them. There are different ways how you can account for these interactions, but the one that we have at the moment is somewhere in the middle in terms of physical, in terms of closeness to the physical reality. And it's so-called electrostatic embedding. So in electrostatic embedding, the charge density of the QM subsystem is polarized by the point charges of the classical MM atoms, but these classical point charges are static, so there's no polarization going on at the side of the MM subsystem. And basically, the way we evaluate this is just a simple Coulomb interaction, but the issue is that, especially in plane wave-based QM codes, and MiMiC was originally designed to work with these, this can get very expensive. Evaluating terms like this, so here we see an energy, QMMM energy term, this can get really expensive really fast. And the reason for this is that for each here we have the sum over all the classical point charges, and for each of them, we need to evaluate the integral over the entire charge density. And since these type of codes store these quantities like charge or electron density on real space grids, with number of grid points in the order of magnitude between millions and tens of millions, and typically in the MM subsystem, we have number of atoms between tens of thousands up to millions. This gets expensive really fast. So what we do in MiMiC is that we implement this generalized embedding scheme that was originally proposed by Lyra and others in the early 2000s, where you split the atoms into two groups based on the distance criterion. So you have short-range atoms that interact explicitly with the charge density of the QM region, like we've seen in the previous slide. And then you have long-range atoms. And these long-range atoms only interact with the multiple expansion of the charge density in the QM region. And this drastically reduces the number of integrations we need to perform in each MD step and saves a lot of time. The generalized part of this is that in MiMiC, we implement this scheme with equations that are implemented in this open-ended way, meaning that compared to the original scheme where you could have control the approximation with only one parameter, that is the short-range cutoff radius, now we can control it also the multiple expansion order. And that gives users quite a lot of flexibility because they can tweak these parameters so that they can perform simulation as accurate as it would be with the full short-range treatment, but at the same time saving a lot of resources. So here we see like demonstration of how you can adjust these parameters for a system of about 140K atoms. And both plots show the effect of changing those parameters. The x-axis lists different cutoff radii, and the color gradient represents the different multiple expansion orders for the long-range treatment. So blue being the no multiple expansion correction, and 8 being the of the maximum order here that is here plotted. So in the plot on the left, we see the maximum error in forces with respect to a reference calculation. And here the reference calculation is the one where we would treat all the atoms as short range. You can see that without any long-range correction, this maximum error decays quite slowly, but only when we move, let's say, towards to some fifth or sixth sixth order, the multiple expansion, we are able to achieve accuracy that's virtually the same that we would have with the full short-range treatment. On the right, we then see that the time that MiMiC spends on computing the QMM interactions as a percentage of the same time that would be required in the reference calculation, meaning the full short range. And you can see that for the accuracy that is close to the one of the reference calculation, using this scheme, we only use somewhere between 1 and 2% of the time that we would use if we wouldn't use it. A lot of use there. Yeah, anyway. So since MiMiC involves like juggling data between multiple different programs, I think it's now kind of useful to describe a little bit how the workflow of this goes. And so let's have a look at the workflow of the electrostatic embedding as implemented in MiMiC. So first, because when you launch, MiMiC has no prior information about the individual subsystems because it's coupled to the MD driver. It only has information about how you'd like to perform the MD part of your simulation. So in the first step, MiMiC collects data from these external programs and uses this information to allocate data structure in the MD driver. So once we are set to go, we get to the main MD loop. And in that one, we always start with updating the coordinates of the system. So once we have a new set of coordinates, MiMiC will transfer these respective coordinates to individual client programs or external programs, MM and QM. and then proceeds to perform the calculation. So at the side, that's fairly simple because you only need to evaluate your forces and energies from this classical force field. On the QM side, it's a bit more tricky because first you need to compute the polarizing potential that is introduced to the calculation. Then you solve the QM equations, which typically are quantum equations, at least in our case. And once these are solved, you send back the electron density to MiMiC that uses this information to evaluate the QMMM contributions to energies and forces. And finally, MiMiC will collect forces from all the parts of the calculation, uses these forces to update velocities, and then updates the coordinate and starts from the new or start the new MD step. And since in the short range, long range scheme, we're using distance criterion for putting the atoms in either the short range or long range groups, and everything's moving every now and then, which is again user specified parameter. You tell MiMiC to resort the atoms so that the approximation we're making is still valid. All right, so let's have a look how it would look like if you were to perform your very first simulation with MiMiC. I'll get an idea how it actually works, and that you need to be not to be afraid of these many different inputs. So indeed, for simulation, here we have a subsystem where system where the QM subsystem will be treated with CP2K, MM subsystem will be treated with GROMACS. And for that, we indeed need, MD as an MD driver, we will use CPMD. So for that, we need 4 input files. One of the core principles of MiMiC is not to touch the inputs of the external programs too much. So we try to keep the setting up the system as simple as possible. So for those of you who use GROMACS, you know that first you need to create this TPR file that you get from using the GROMACS preprocessor. Sorry, that sorry about that. From the GROMACS preprocessor. And for the input, you basically only need to specify the integrator, which is not MD or energy, but you use MiMiC. And then you need to provide an index file where you specify this atom group labeled by name of your choice. Those will be the QM atoms in the simulation. And then you need to specify the name of this index group or atom group in the input, and you get your TPR file that's MiMiC ready. For the CP2K, it's, I would say, even simpler because there you only need to specify the runtime, it's MiMiC. You can keep all the rest like you would be performing the normal simulation with CP2K. Only that at the moment on the QM and QMM side, we don't support periodicity, so this needs to be an isolated system or modeled as isolated system. So that means that you need to choose the Poisson solver accordingly. Finally, we get to CPMD and MiMiC. So CPMD is the MD driver, and you can see that here we have only keywords that set up MD related parameters like time step or a maximum number of steps or thermostat. And then we run MiMiC in the mode MD. The reason for this is that you can also use CPMD to serve as external program that provides QM energies and forces, but here we run it as an MD driver. And then we specify the input file for MiMiC. This is optional because it actually defaults to MiMiC TOML, which already also gives away the fact that for MiMiC input, we're using TOML language. that we found quite convenient for this purpose. And here I'll just briefly describe what we are actually defining here. So we have the box where we specify that we want to use the same box as is used like for the simulation and MD driver, want to use the box of the same size as subsystem 2, which kind of makes sense because that's the larger subsystem here. Then we need to determine the overlaps between certain particles in the MM and QM subsystem. We do that automatically. And then the last part describes the parameters of the QMMM electrostatic embedding scheme that we talked about in the previous section. So once you launch it, once you launch it with this as an MPI MPMD job, with this MPI run call, or now with the newer versions of Slurm scheduler, you can use also srun in the same manner. You're set to go. Once everything is running, you can of course track the outputs of the individual client external programs, but since MiMiC is the actual only simulation component that has all the information about all parts of the simulation, we also provide, I would say, somewhat convenient output. So in the initialization phase, it first prints all the information about all the subsystems. Here, as an example, I'm using the QM subsystem treated by CP2K. You can see that there are 10 particles simulated. This is the box that is being used by CP2K. And then I mentioned that we determine the overlaps automatically, and the information about the determined overlaps is printed here, and the user can inspect those and just make sure that everything is set up correctly. Then once you're running the simulation, we have this convenient output where you can track the energies and temperatures of the individual subsystems, interaction energy, and then the collective energy of the entire system, be it potential, total, or if you run NVT simulation, also the conserved energy. Finally, you've seen the benchmarking in an example of this electrostatic embedding as done in MiMiC. And this can be quite tricky, so we're trying to automatize as much as possible. And one way we're doing this is also you can automatically perform this benchmarking. So only thing you need to do is set this run benchmark keyword to true, and then instead of cutoff distance multiple orders, which are scalars, you supply vectors with different values, and then MiMiC will perform reference calculation with no long-range approximation and all the combinations of these parameters. And you can nicely see the errors in energies, mean errors, and maximum error in forces corresponding to different settings. So the one thing that happened over these past few years was this major refactoring and of the entire framework. It was kind of coming from our desire to be able to interface external QM programs just as easily as it was for the MM programs. And the particular motivation for this was the introduction of CP2K into the MiMiC ecosystem. And here in the next few slides, I'll show you some results from the paper we got recently published on this that demonstrate, or I think it demonstrates these three properties. So starting with stability, here, if you focus on the orange line, you see the fluctuations of the total energy per particle for systems of different sizes. The uppermost is the smallest one of some 3,000 atoms up to 440,000 atoms in the last one. And with the blue lines here being for comparison, and these come from the pilot implementation of MiMiC that only used the combination of CPND and GROMACS. And you can see that all these lines are stable with no drift that is observable at all. The next one is the modularity, and that was actually quite nice because once we performed these simulations, we were able to get like new interface virtually for free. So we performed the simulation that were just as stable with the CP2K as a QM client and OpenMM as the MM client, and virtually for free just because someone had to write the OpenMM interface, which was PhD student Andrea Levy from our group. And once the interface was there, it was basically trivial replacing this simulation component with another. Finally, I think MiMiC is efficient and kind of do no harm, say, summarizes its main design principle, meaning that we want these external programs to perform just as well as they were used in a standalone simulation. So these plots, in these plots, you can see, or better, you can't see 6 different lines because they overlay. For simulations performed with CP2K, and these are, just to clarify, these are not QMMM times or anything, these are just timings and scalings for the simulation for the QM part, which is typically the most expensive part of the QMM simulation. And yeah, you can see that that the performance of CP2K is unaffected regardless whether they were performed with CP2K alone or in QMMM setting with MiMiC. Finally, the original purpose of this interesting plot was that we wanted to demonstrate that in increasingly distributed simulations, the communication doesn't really affect the performance because we introduced quite a lot of additional communication in MiMiC during this refactoring. And and we also demonstrated something else. So for these, for all of them, we use the same QM subsystem with a cubic box, roughly with 400 grid points per site. So I would say reasonably sized. And then we had 2 different MM subsystems. So the donut plot array on the left comes from simulations performed with small MM subsystem of about 3,000 atoms. The one on the right one of about 100, I think 100,000. Yeah, sorry, that's written there. 100,000 atoms. And you can see from this simulation that actually, I'll take the one that was the most efficient one, that even though we were treating like 30 times as large overall system, it resulted only on like less than 5% increase in time that is spent per MD step on everything. So that's neat, I would say. So now for those who are interested about what's under the hood of MiMiC, we'll have like brief overview of how it's actually implemented, what it takes to interface external program and so on. So MiMiC as a framework is designed, or its philosophy is to interfere minimally with the code while allowing maximal flexibility of using different external programs. And to be able to do this, we decided to split the framework into 2 libraries. So there is the main library that is linked to simulation driver that runs the MD simulation and propagates the system in time, and that's MiMiC main library. This is the part that controls the simulation, collects the information and about subsystems and compute interactions. But for the external programs, you only need to use MCL, which is this very lightweight communication library. So the MiMiC is written in Fortran. Just if you're interested, the MCL is written in C++, but we provide APIs in C++, C, and Fortran for MCL. So we are quite flexible in that respect. And the point of MCL is that it kind of provides some sort of an abstraction layer on top of the actual communication mechanism it's used. I talk about so far, and I will keep talking about MPMD type of running of MPI jobs, because at the moment it's the only communication mechanism that we support. But the thing is, this could be, once the interface is written, this could be new communication mechanisms could be implemented in MCL without affecting the API. And for MPMD MPI jobs, during the initialization, it looked like this. So you launch the program with a single MPI run, and all the and all the executables share the same world communicator. And right after calling MPI init in these programs, this needs to be intercepted by equivalent MCL initialize that will split this world communicator and return these local world communicators that internally serve as a world, and meaning that for those programs from the inside, they are unaware of that or of the existence of other programs. And then the communication between them is through intercommunicators that are stored in the objects in MCL. Yeah, on the client program side, because I mentioned it several times, but it makes sense really. But now I introduced that we actually operate on this client server or server client base, where server, which is the main library, coordinates or gives requests to client programs that are then acted upon. So you can see here that basically in every step, the server issues a request, and client then executes the request. And typically there are four types of those. You can run a calculation, you can send some data from client to server, and vice versa, receive some data. And then there's a special type of request, exit, to terminate the run. And regarding the actual implementation, the easiest way is just to write a conditional loop like this on the client side, where you receive the request, execute the action or the requested action, and upon reception of the MCL exit request, you terminate or exit the loop. Then the MiMiC, since it's conceived to be modular, we try to that this modularity is also reflected in the way it is written. So you have the main module that contains the API of the main library. So here, just bunch of functions like setters, getters, runners, kind of thing, and then there this system object that contains all the information about the system, the simulation box, interaction between subsystems or individual subsystems, each of which is linked to one of the client programs participating in the simulation. And if we go deeper and look at the interaction type object, you see that we store the settings for these interactions. This is the QMM interaction we've seen before, and then the list of these short range and long range atoms for computing the interaction terms. And finally, we have different subsystems, which I suppose all of them will kind of contain some sort of particles, atoms for MM, nuclei for QM, and for the QM on top of that we need some objects to store these grid-based quantities like densities or external polarizing potential. So they're there. So in the final part of this presentation, I would like to talk a little bit about development that's already there, that's going on, and so on. So first of all, given the nature of the whole project, we are highly dependent on functionalities in these external programs. So the pilot version of MiMiC only involved CPMD and GROMACS, and it was written mainly by Magnus and Slava here. And recently, during the refactoring efforts, we included also CP2K. We have OpenMM. Then, in quite advanced stage of development is the interface to Quantum Espresso. So far, again, not for the periodic QMM, only for isolated systems. And then Tinker HP, which is particularly interesting, and that was written by a PhD student or former PhD student of Magnus, Sonata Kudravichute, who was working on introducing the polarizable embedding into MIMIC. And to explain how it operates, first let's have a look at the normal electrostatic embedding workflow. And to have like full back polarization between the MMQM subsystem, we expand this solve QM equation step to have another communication loop, and that is this. So to implement this QM amoeba model, we need to, in each SCF iteration of the SCF calculation, we need to pass the density to MIMIC that uses it to compute the QM field on the M atoms. That then is used to solve these polarization equations in the amoeba supporting MM client. And once we receive these induced dipoles, we use them to update this external potential and perform the next SCF iteration in the QM client. Apart from this, we have quite a lot of other things going on. So you can see that Andrea is actually quite industrious PhD student because there are already like two other projects he is involved in. And one of them is that he recently introduced the Python API to MCL, which allows us to create couplings with with different code written in Python. And one of such that is interesting, and David is working on introducing it into the ecosystem, is VeloxChem, which is the electronic structure program that is known for highly efficient use of GPUs. And then the other project of Andrea was the introduction of these DREST charges that are computed directly in MIMIC. And these are the charges that are dynamically generated during the run to reproduce the electrostatic potential that is generated by the QM region. And he also generalized this to higher multiples, which will be like a new feature and could be quite useful to, for example, for adding like additional layer between these short and long range schemes of doing electrostatic embedding, or on something that Sachin's working on, and that is the re-implementation of the force matching scheme from that was originally there in CPMD. Then another interesting project is from our former PhD student François Mouvet, who was working on an adaptive MLMTS. So for those of you who are not familiar how multiple time step dynamics work in QM or QMM context, so it allows you to perform MD dynamics with systems that are propagated with some low-level method, and you only need to perform high-level calculation using high-level method or level of theory every now and then. And the ML approach here was to push these individual steps where you need to perform high level as far as possible by training the model on the difference between the two levels of theory. And he introduces into the pilot implementation of MIMIC, but now our current PhD student, Thibaut Clay, is working on reintroducing it into the new version, and it could be later and the delta ML could be later replaced by direct ML, also thanks to the contributions of Andrea. So very quickly, another interesting client that Bart's working on is this DFTFE, which is a very scalable DFT code based on finite element basis set. And Fernando is introducing the surface hopping dynamics in the QMMM context to MiMiC. So one really cool thing about this entire thing is that once it's implemented in MiMiC, it should be available with all the other codes that are interfaced with MiMiC. So, and this includes the polarizable embedding. Finally, there are a few other developments going on at the same time. One is that we are trying to make better use of GPUs by offloading these short-range interactions, which are the most expensive part on the QMMM side. So that should significantly decrease the requirements when running calculations. Then for developers, we would like to offer APIs for both MCL, where we already have them, and MiMiC. It will be considered to be like holy trinity of computational physics or chemistry. That is Fortran, C++, and Python. And finally, after the refactoring effort, we are starting to work on implementation of the new multiscale and multi-layer models, like different QM embeddings and maybe QMMM, and so on, up to potentially Continuum. So I hope that you were interested, at least something, what I had to say, and we plan the new release hopefully within a few months. So if you're a potential user, stay tuned for this. And if you're interested about more information or getting more information on MiMiC, last year we published this paper that summarizes everything quite nicely. Last but not least, in some 3 weeks, we're organizing this summer school focusing on MiMiC. So if you'd like to get some hands-on experience, the registration is still open until the end of this week. So yeah, there's that. Last but not least, this is like communal effort. And even though MiMiC kind of everything started in Ursula's group like 9 years ago with Magnus here and Simone over here. We grew over the years, and basically nowadays the main development efforts are taking place in Magnus's and our group, but there are many people who contribute to the other efforts. However, I would like to give shout out to Slava Bolnik, whom I mentioned, contributed quite a lot in terms of coding in the initial stages of the development, and who was at the time a PhD student, Pavlos Karloni's group. So that's it. Thank you.
Thank you very much, Andrei. So if people, you say, stay tuned, how they can follow you?
Yes, there is in the upper right corner over here, there's our website where you can also subscribe to some sort of newsletter. It's not very updated. We're working on updating it so that it kind of follows all the new developments and so on. But once it's there,
okay, so you suggest people to follow you via the web page. That is what is your int.
That's one approach. Other is typically Magnus posts quite a lot about MiMiC when there's something new on LinkedIn. So if you're a fan of that, be my guest. And but yeah, I think this email list would be the best way.
Yeah. Okay. Thank you very much. And we have a couple of questions. The first one is Alexandro Munez. Alexandro, I tried to allow you to talk. please let me know if you can. You should be able to speak now. Okay. I guess he cannot speak because, yeah. So Alexandra will read the question for you. So just let me remove him. Okay, so I have been working with computational methods to analyze the formation of protein ligand and protein-protein complex. What will be the application of MiMiC to analyze conformational change in this complex?
Conformational change, as I said, at the moment, we are mainly focused on the QMMM. So I feel like, and I don't have that much experience with application, but I feel like it's not exactly suited for this right now. But eventually, I'd like to introduce something that might be useful for you as well. It was kind of not an answer, but that's
Okay.
all I can say.
Thank you. And then we have another question that is that you mentioned that MiMiC can be also used to couple coarse-grain simulation with atomistic MD simulation. Can your flame handle hybrid regions where there are both coarse-grain atomistic atoms? So I mean, hybrid region where you have both coarse-grain atomistic. If so, how do you handle that?
So that's the thing. This is a question on a particular implementation, and what we provide right now is a framework. So again, I am not familiar with coarse grain force field approaches. I know that there are these approaches where you perform simulation with coarse grain, and then you try to reconstruct the higher resolution. And the thing is, in principle, it can be implemented, but right now, no one is really giving thought to this particular type of interactions. So I can't really give you educated answer to that either.
Okay, thank you. Could you maybe point someone?
Right now, I think I have quite good overview around who is involved. In principle, as Magnus is the main maintainer, he might have some ideas about who would, in principle, could be interested in doing so, but like implementing this type of interaction. But I don't think there's anyone right now. So.
Okay, thank you. We have now a question from Jorges that they ask where he can subscribe for the workshop. Maybe you have a web page or something.
Yes, sorry.
You can put in the chat if you have it, maybe, or in the forum if you prefer.
Yeah, I'll add it to the forum. So it's a CCAM organized workshop with some support from Psyche. So you can do this via CCAM website, but I'll add it also to the forum so that it's nicely in one place.
Thank you very much. Now we have a question of Diego. I allow Diego to speak if he wants. No. So we
Hello, can you hear me?
Please go ahead, Diego. Sorry.
Yeah, yeah. Thanks for the talk. I was wondering if it would be possible right now, or maybe in the future, to couple MiMiC to some external libraries such as Plumed. I was thinking maybe.
That's a good question. At the moment, we have kind of support for Plumed because it is the enhanced sampling is kind of taken care of through the MD driver. So we have a build of CPMD with MiMiC and Plumed interface. But what I have in mind, and when there is time for that, we could, in principle, couple it directly with MiMiC because before the information gets passed to the MD driver, you can already bias your forces, and so in principle, I would aim to have the interface directly in MiMiC, and when someone is up to it, definitely.
Well, thank you very much.
Over.
Thank you. So we have another question of Stefano. So I will try to ask Stefano if you want to ask himself the question. Please, Stefano,
Yes,
if you can, you can speak. Please go ahead.
hello, can you hear me?
Yes.
Yes.
Thank you for the workshop. I would like to ask you if do you have some case study that you could show us?
A study applying MiMiC.
Yes.
Okay, so we have quite a few studies coming mainly from Paolo Scarloni's group, who used this old pilot version that was somewhat different, not as flexible, and this involved simulations with CPMD and QMMM. CPMD and GROMACS, and in QMMM setting. Right now, we are starting, because we only finished the implementation efforts on this refactored version. We are starting to running like new kinds of studies using MiMiC. So again, stay tuned, but I can put some references for studies performed with the old version to the forum.
Can you send us the reference?
Yes,
Thanks. Thank you very much.
I'll just make
So
note.
I think Andrei will post information of the summer school, information of the reference on the forum Ask Bioexcel. So if you go to see askbioexcel.eu, you will find the information there under the webinar post.
Okay, thank you.
Yeah. So because we have also a question about if the workshop will be in person. So I think it will be great if you can post more information there concerning the. So please, you will say something.
Go ahead. I'll just write down what I'm supposed to post.
Okay. So we do not have any more questions. So I would like to, if you could just give me the screen again, so I could just make a final announcement. If nobody typed any question in the meantime.
Stop sharing now.
Yes, so I will just go back. So just wait. I think I have to share again. Yes. So as usual, as a final, I want to just tell you that this is the last Bioexcel webinar of the spring series, and then we will come back with the autumn series in September. So please go on to follow us. We have other activity going on in this period. You can find all the activity in our webpage. And I want to thank you again, everybody of you, for attending the webinar, and Andrei for being here with us. And I will meet you in September. Okay. Have a nice summer. Bye-bye.
Thank you for having me. Bye.